Every morning, the weather forecaster sits down with two things: yesterday's forecast and today's radar data. Yesterday said 70% chance of rain. Today's radar shows scattered clouds. Time to update. This is Bayesian inference. The prior is what you believed before seeing the data. The likelihood is how well the data matches each possible state. Posterior is your updated belief. Welcome to the weather forecaster. Yesterday's forecast, 70% chance of rain. That's the prior. A forecaster new to the city has a wide, uncertain prior. A veteran has a narrow, confident prior. An uninformative prior is flat. A weakly informative prior nudges toward reasonable values. An informative prior reflects domain expertise. Choosing the prior forces you to state what you knew before the experiment. Today's radar streams in. The likelihood asks if it is going to rain. How probable is this radar pattern? Strong data gives a peaked likelihood. Ambiguous data gives a flat likelihood. The likelihood is determined by data and model, no subjectivity. Prior times likelihood equals posterior. Wide prior and strong data, posterior follows data. Narrow prior and weak data, posterior follows prior. The posterior is always a compromise between what you knew and what you just learned. Sometimes the math stays clean. Beta prior plus binomial data equals beta posterior. Just update the shape parameters. No integration needed. Normal plus normal equals normal. Gamma plus Poisson equals gamma. Conjugate priors give closed form posteriors without magma. Today's posterior becomes tomorrow's prior. Day 1, wide bell. Day 7, tight. Each day of data sharpens the forecast. Beliefs converge toward truth as evidence accumulates, regardless of starting point. Bayesian update cycle. Prior, likelihood, posterior. Conjugate priors for clean math. Sequential updating for accumulating evidence. Next, how to check if the forecast is trustworthy.